Imagine a home where thick interior walls absorb heat during hot days and release it during cool nights, where outdoor temperature swings of 40 degrees produce indoor variations of just 3 to 5 degrees, and where heating and cooling bills run 60% below conventional construction in the same climate. That's not a theoretical ideal or a future technology concept. That's the documented performance of homes built with properly designed thermal mass walls. The underlying principle is simple enough that ancient civilizations exploited it thousands of years ago. Thick walls made of stone, earth, adobe, or similar dense materials store substantial quantities of heat. The storage capacity creates a thermal buffer that moderates interior temperatures across daily and seasonal cycles. Modern implementations using concrete, masonry, or specialized thermal mass materials produce performance matching or exceeding ancient precedents. The catch is that thermal mass construction costs somewhat more than conventional framed construction initially. The payoff comes through decades of reduced operating costs and dramatically improved comfort. Understanding how thermal mass actually works, what applications suit it, and what limitations apply enables informed decisions about whether this approach makes sense for specific homes and specific climate conditions. The fundamental physics of thermal mass involves the specific heat capacity of dense materials. Water possesses the highest specific heat of common building materials, though practical building applications typically use stone, concrete, brick, adobe, and rammed earth. These materials store 15 to 35 BTUs per cubic foot per degree of temperature change. A typical thermal mass wall containing 150 cubic feet of dense material stores 2,250 to 5,250 BTUs per degree of temperature change. This substantial storage capacity absorbs heat during warm periods and releases it during cool periods, moderating indoor temperature swings significantly. The time lag effect that thermal mass produces creates the daily moderation that makes these walls so effective in appropriate climates. Heat arriving at the exterior surface of a thick thermal mass wall travels slowly through the material, arriving at the interior surface typically 8 to 14 hours later. In climates with substantial daily temperature swings, this lag produces an important dynamic effect. Peak outdoor heat during hot afternoons reaches interior spaces overnight, when outdoor temperatures have cooled. The heat then dissipates through nighttime ventilation, or radiates to cooler nighttime outdoor conditions, rather than adding to indoor heat load during the hottest hours. The lag effect is particularly valuable in desert climates, where daily temperature swings of 30 to 50 degrees are common. Carlos Mendoza, a New Mexico-based architect who has designed over 80 residences, incorporating thermal mass wall systems, has documented the performance patterns across his portfolio. His typical design uses 12 to 18-inch thick adobe or compressed earth block walls for exterior construction. Homes built to these specifications in southwestern climates show annual heating and cooling costs averaging $400 to $900 compared to $2,200 to $4,500 for conventional construction in the same climates. The annual savings of $1,500 to $3,500 continue across the home's lifespan, producing cumulative savings that substantially exceed the initial cost premium for thermal mass construction. The historical precedents for thermal mass construction span virtually all ancient civilizations in appropriate climates. Egyptian mud brick construction, Roman concrete structures, Chinese rammed earth walls, Native American adobe pueblos, Middle Eastern stone construction, and countless other traditions developed thermal mass techniques suited to local materials and conditions. The consistent reappearance of thermal mass approaches across different cultures confirms the underlying effectiveness, rather than representing coincidental choices. Where materials permitted and climate justified the approach, civilizations independently developed similar techniques. Madeleine Richthofen, an architectural historian specializing in traditional construction, has extensively documented how thermal mass principles influenced vernacular architecture across different regions. Her work at various historic sites shows how building traditions evolved to match local climate conditions through careful thermal mass design decisions. Desert civilizations built thick walls with minimal openings to maximize thermal moderation. Temperate civilizations combined thermal mass with larger openings to balance thermal moderation with natural lighting and ventilation. Each tradition represents refinement across generations that produced buildings matching their climate requirements with remarkable precision. The material options for contemporary thermal mass construction provide substantial flexibility. Traditional adobe offers authentic appearance and proven performance, but requires specific climate conditions and construction expertise. Compressed earth blocks produce similar thermal performance with somewhat simplified construction approaches. Structural concrete masonry units with solid grouting provide thermal mass with standard construction techniques. Poured concrete walls offer maximum flexibility but require substantial formwork investment. Rammed earth provides outstanding performance with very high construction labor requirements. Each approach suits different priorities, budgets, and construction contexts. The integration with passive solar principles produces substantially enhanced performance. Thermal mass walls positioned to receive winter sunlight absorb solar energy directly, storing it for release during cold nights. This integration transforms thermal mass from purely a moderating influence into an active heating resource. Proper passive solar design with integrated thermal mass can eliminate 50 to 80% of typical heating requirements in appropriate climates. The combination of solar gain capture, thermal mass storage, and daily temperature cycling produces dramatic performance improvements over either passive solar or thermal mass alone. Ricardo Velázquez, a passive solar designer practicing in Colorado, has conducted detailed performance monitoring on 14 homes combining thermal mass walls with careful passive solar design. His measurements show heating load reductions of 60 to 78% compared to conventional homes in equivalent climates. Annual heating costs average $180 to $450 for these homes in climate zones, where conventional construction typically incurs $100 to $800 to $3,500. The cooling load reductions average 50 to 70% through the same thermal mass moderation and related design features. The combined heating and cooling savings typically exceed $2,500 annually in these installations. The thermal mass location within the building envelope affects performance substantially. Interior thermal mass exposed to solar gain and living space provides maximum benefit for combined passive solar and thermal moderation applications. Exterior thermal mass insulated from interior spaces provides minimal benefit and should be avoided. Thermal mass within the building envelope, but insulated from exterior conditions, serves interior thermal moderation effectively. The positioning decisions matter as much as the material selection for achieving intended performance outcomes. The cost analysis for thermal mass construction involves comparing initial construction premium against operational savings across the building lifespan. Thermal mass exterior walls typically cost 15 to 35% more than conventional framed walls, representing $40,000 to $120,000 additional dollars on typical home construction. The annual operational savings of $1,500 to $3,500 produce simple payback periods of 15 to 40 years in most applications. For owners planning long-term occupancy, the economics favor the approach despite the initial premium. For owners planning shorter occupancy periods, the investment may not recover before sale. The interior environmental quality benefits of thermal mass homes provide qualitative improvements beyond pure energy performance. Interior temperatures remain remarkably stable throughout daily cycles, eliminating the temperature swings common in conventional construction. Interior humidity tends toward moderate stable levels, as thermal mass materials buffer moisture, as well as temperature. Interior air quality improves due to reduced infiltration and reduced moisture variations that support mold growth. The acoustic performance of thick masonry walls substantially exceeds conventional construction, producing quieter interior environments. The cumulative qualitative improvements often matter more to occupants than the pure energy savings. The construction considerations for thermal mass walls require specialized expertise that varies with chosen material systems. Adobe construction requires skills increasingly rare in contemporary construction, but still available in regions with continuing Adobe traditions. Rammed earth requires specialized equipment and experienced crews. Concrete masonry offers broader contractor availability, but requires thoughtful thermal engineering to optimize performance. Poured concrete walls offer flexibility, but require substantial formwork investment. Selecting the appropriate material system requires matching chosen approach to local contractor capability and project budget. Elena Stephanopoulos, a sustainable construction consultant based in Arizona, has documented common implementation pitfalls that compromise thermal mass wall performance. The most frequent problem involves insufficient wall thickness, typically 6 to 8 inches, rather than the 12 to 18 inches that optimal thermal mass design requires. The thinner walls provide insufficient thermal storage for proper daily lag and moderating effects. Second is incorrect thermal boundary placement, with insulation placed on interior surfaces, preventing the thermal mass from interacting with interior conditions. Third is inadequate integration with passive solar design, leaving thermal mass walls in shaded positions that never receive solar gain. Avoiding these common errors substantially improves performance outcomes. Now for the obstacles and limitations that affect thermal mass wall applications. First, the climate suitability varies substantially across different regions. Thermal mass performs excellently in climates with substantial daily temperature swings, reliable heating season solar gain, and moderate humidity levels. Climates without significant daily temperature variation produce minimal benefit from thermal mass, since there are no temperature swings to moderate. Humid climates can produce moisture problems within thermal mass materials if appropriate waterproofing isn't provided. Northern climates with limited winter sunshine cannot capture sufficient solar gain for passive solar contribution. Matching the approach to appropriate climate conditions is essential for successful performance. Second, the structural engineering requirements exceed those of conventional construction. Thermal mass walls carry substantial loads due to their own weight as well as typical building loads. Foundations must be sized for these loads, rather than lighter framed construction. Seismic design for thermal mass structures requires careful attention in earthquake zones. The structural considerations add to the overall cost premium and require engineering expertise not universally available. Third, the construction timeline for thermal mass buildings often extends beyond conventional construction schedules. Adobe, rammed earth, and similar approaches involve wet materials requiring cure time. Masonry construction proceeds at slower rates than framing. The extended timelines create carrying cost increases during construction and delayed occupancy that affects project economics. Fourth, the insurance and financing considerations for non-conventional construction create practical obstacles. Some insurers charge higher premiums for thermal mass homes due to limited experience with these structures. Some mortgage lenders decline to finance alternative construction approaches or apply unfavorable terms. Finding appropriate insurance coverage and favorable financing requires effort that conventional construction doesn't require. Fifth, the resale market considerations for thermal mass homes vary across different regions. Southwestern markets with established thermal mass traditions often value these homes at premium levels. Markets without established traditions may value them at discounts reflecting buyer unfamiliarity. Homeowners must consider their intended ownership period and local market conditions when evaluating whether thermal mass construction makes financial sense for their situation. Despite these considerations, thermal mass construction offers proven performance for appropriate climates and committed long-term owners. The combination of reduced operating costs, superior comfort, and connection to proven traditional approaches appeals to buyers seeking alternatives to conventional construction. The environmental implications of thermal mass construction include both benefits and considerations. The reduced operational energy consumption produces substantial lifetime carbon savings compared to conventional construction. The embodied energy in producing thermal mass materials varies substantially based on specific materials and sources. Local earth-based materials produce very low embodied energy, while Portland cement and manufactured masonry units have higher embodied energy. The overall environmental balance typically favors thermal mass construction, even accounting for embodied energy, particularly when locally sourced traditional materials are used. The durability performance of thermal mass walls substantially exceeds typical conventional construction. Adobe walls in New Mexico have lasted 400 years and remain structurally sound. Roman concrete structures have stood for 2,000 years. Traditional, stone masonry can exceed 1,000-year lifespans with appropriate maintenance. Contemporary thermal mass construction follows these traditions, with properly designed homes showing minimal structural deterioration across centuries rather than decades. The extended building lifespans produce environmental benefits beyond the operational energy savings, as fewer replacement construction cycles over extended timeframes reduce cumulative resource consumption and waste generation. Franz Klemmer, a German architect who has designed passive houses and thermal mass homes across Central Europe, has conducted comparative performance analysis between various design approaches. His documentation shows that properly executed thermal mass construction in appropriate climates produces lower operating costs than certified passive houses that rely primarily on super-insulation and heat recovery ventilation. The finding challenges common assumptions about which approaches produce maximum performance, showing that traditional thermal mass principles remain competitive with contemporary, high-performance approaches when appropriately matched to climate and site conditions. The potential for hybrid approaches combining thermal mass with contemporary construction techniques opens possibilities for homeowners seeking some benefits without committing to full traditional construction. Interior thermal mass accents, including masonry fireplaces, tile flooring over concrete slabs, and masonry feature walls, provide partial thermal mass benefits within otherwise conventional construction. Phase change materials integrated into wall systems provide substantial thermal storage within thin wall assemblies. Water-based thermal storage in contained elements like trombe walls or water wall systems offer flexibility unavailable with traditional dense materials. These hybrid approaches let homeowners capture meaningful thermal mass benefits without committing to complete thermal mass construction. The adaptation of thermal mass homes to lifestyle patterns differs from conventional construction in ways worth understanding before committing to the approach. Thermal mass homes respond slowly to thermostat changes compared to conventionally constructed homes. Raising desired temperatures for arriving guests requires several hours of lead time rather than the quick response conventional homes provide. Cooling set point changes similarly require advanced planning rather than immediate adjustment. Families living in thermal mass homes develop operational habits that work with the building's thermal characteristics rather than against them. Most families adapt easily to these patterns and come to appreciate the stability of thermal mass performance, though initial adaptation periods sometimes cause adjustment concerns. The combination of thermal mass with contemporary insulation technology has produced substantial performance improvements over purely traditional approaches. Modern insulation materials placed on the exterior of thermal mass walls maintain interior thermal coupling while dramatically reducing heat loss to outdoor conditions. Vapor barriers prevent moisture intrusion that could compromise thermal mass materials. Air sealing details prevent infiltration losses that pure traditional construction couldn't address. The integration of traditional thermal mass with modern envelope technology produces performance exceeding either approach alone, while maintaining the essential benefits that make thermal mass worthwhile. Isabella Cortez, a Mexican-American building scientist who has documented traditional adobe construction performance across historic structures in the American Southwest, has found that properly maintained 300-year-old adobe homes continue delivering thermal performance matching or exceeding most contemporary construction. The aged structures show minimal degradation in thermal properties despite centuries of use. This multi-century performance documentation provides compelling evidence for the long-term validity of thermal mass construction, demonstrating that these buildings continue performing as intended across timeframes that dwarf the expected lifespans of conventional construction. The maintenance requirements for thermal mass construction typically prove modest, despite occasional concerns about traditional construction complexity. Adobe and earth-based materials require periodic reapplication of exterior surface finishes every 5 to 15 years, depending on exposure conditions. The maintenance work typically proves manageable for motivated homeowners performing the work themselves or reasonable when hired out periodically. Masonry and concrete thermal mass construction requires essentially no maintenance beyond standard exterior coating renewal on schedules similar to conventional construction. The maintenance intensity typically proves less demanding than common assumptions suggest, particularly compared to the ongoing equipment maintenance that conventional construction's mechanical systems require. The market development for thermal mass construction continues evolving as awareness spreads and successful examples accumulate. Specialized contractors have developed in regions where demand has grown sufficiently to support full-time practice. Supply chains for appropriate materials, including compressed earth blocks, specialty thermal mass concrete products, and related items have expanded beyond traditional adobe regions. Architectural firms with thermal mass expertise have emerged throughout the country. The growing infrastructure makes pursuing thermal mass construction substantially easier than it was even a decade ago, with lower costs, better availability, and more refined techniques emerging continuously. The fire resistance characteristics of thermal mass construction provide additional safety benefits worth noting. Adobe, earth block, concrete, and masonry walls offer fire resistance measured in hours rather than the minutes typical wood framing provides. Homes in wildfire-prone regions benefit substantially from these fire-resistant characteristics. Insurance premiums in wildfire zones sometimes reflect these reduced risks through favorable rates for thermal mass construction. The protection against wildfire exposure has become increasingly valuable as wildfire frequency and intensity have grown across the American West and other fire-prone regions. The pest resistance of solid thermal mass walls exceeds wood-framed construction substantially. Termites, carpenter ants, rodents, and other structural pests find no suitable material to attack in solid earth, adobe, or masonry walls. Homes built with these approaches eliminate entire categories of maintenance concerns that plague conventional construction in many regions. The long-term implications include reduced pest control costs, elimination of structural damage from pest infiltration, and generally more durable performance across the building lifespan. The sound control provided by thermal mass walls transforms interior acoustic environments compared to conventional construction. Traffic noise, neighbor sounds, wind noise, and other exterior acoustic intrusions typically problematic. In conventional homes, become nearly inaudible through thick thermal mass walls. Interior acoustic environments achieve quietness that conventional construction can match only through extensive specialized soundproofing measures. Families moving from conventional to thermal mass homes often cite the acoustic improvement as among the most surprising and appreciated qualitative benefits, though rarely included in initial considerations about construction approach selection. The educational infrastructure for thermal mass design has developed substantially over recent decades. University programs in sustainable architecture teach thermal mass principles alongside conventional construction approaches. Professional organizations maintain design guidelines and reference materials for practitioners. Specialty publications document case studies and performance data. Workshop programs train contractors in appropriate construction techniques. The cumulative knowledge infrastructure makes thermal mass design more accessible than it was even a decade ago, reducing barriers to successful implementation. Consider what properly designed thermal mass construction means for families building in appropriate climates. The additional upfront investment produces a home that works with natural thermal cycles rather than fighting against them continuously. Operating costs remain dramatically reduced throughout the home's lifespan. Interior environments provide comfort qualities that conventional construction cannot match. The structural durability exceeds any practical concern about building longevity. The connection to traditional construction approaches adds cultural depth to modern living. The performance benefits accrue continuously rather than diminishing over time. The economic returns build steadily across decades of reduced operating expenses. The opportunity exists for families in appropriate climates willing to look beyond conventional construction patterns. The knowledge and expertise have matured to support informed decisions. The examples exist across centuries of successful traditional construction and decades of contemporary applications. For the right family in the right climate building with long-term perspective, thermal mass walls offer a path toward homes that genuinely work better than what mainstream construction produces. The principles have proven themselves across countless civilizations and countless centuries. The question isn't whether thermal mass construction works. The question is whether particular circumstances and priorities align with what this approach delivers.